Sujata, for your introduction. And I'm grateful to the TCHS and you, Sujata, for saving me for the last. And I hope I won't disappoint you. And I'm grateful especially for combining the two papers into one presentation slot. Actually, the two papers are really covers the same topic. It's for the IP Swen. Maybe you are not familiar with this diagram, but it's interesting for me. IP protocol extension for too many, especially the younger generations sitting here in APNet 2026. This topic may be some old school, but to all generations, me included, the story of IP versions of castles is really interesting, fascinating, or intriguing. So, I mean, at least I can share my little excitement to some of you for this talk. This one, yeah, this way.
想想，无所谓，是再贴一下是。
Okay, the two papers are about how we scale the old school IPv4 to some useful meaningful way. First is what there's a action test bed version 1.0. What is about a global test bed, and then a prototype how works, how it works. Then at the edge of the internet, when IPv4 packet starts, we need some new ways to bridge the gap. So we choose the CityNet as the starting point, and deploy a method called ISP4x, and how we see this may change the game. So for starters, what is that? This is a passive question for you to test large language models. Is it timely or is it precision? Has precision? The ChatGPT talks quite a lot about this, and mostly it's correct. First of all, IPv4 has the edges. It's a key point. All makes sense if the edges has some meaning. Very simple, valid edges. But the fact of weird thing is it has three forms, like the other two IP versions. It's variable length. So you'll see with the there's a text representation. You just add some dotted decimal after the base IPv4 address up to 7 bytes, and then you store it. You store the address in any IP stacks with fixed length 12 byte structure, and then you use another kind of variabless encoded in protocol messages, such as the BGP update message. These three elements, we call it design principle of this schema. It's variabless because you must keep the IPv4 base address space permanent, including its routing architecture and its address allocations existing in for example in this institutions. And then it must be single stack implement. You can't run multiple parallel stacks, like you update your phone OS on one system, and then you must be binary compatible to existing software API and its numerous applications. This is what the design means. Okay, I'll be quick. This is an evolutionary adjacent extension to IPv4, and it's not have any dependency on IPv6 because no IPv6 here. You can see in this menu, this is the China mobile overlay on Singletel. There's no visits here, and this is the hotel event network. If you dare to turn off IPv4, and immediately you can't live anywhere. So this is the best scenario of prediction. We have to start in a linear projection. So at least in my 70s or 80s, I can't see a full 100% IPv6 deployment. This is the ideal development, and actually the same guy predicts the dual stack model will be permanent, and the IPv4 will be around forever. So let's get into the technical issues. How the packets transit onto this internet. The packets has the format of options. So we build a global test bed prototype version. Now we finished it, so we venture to upgrade this version from 0x.x to 1.0, and we have 4 venture points and additional test control points distributed to different local networks of geologically different space. Then to make this test bed work and to transmit the packets, we need this three packets. For details, please refer to the papers. Basically, it makes BGP work and make the GRE tunneling work and make the routing propagation work. yes, the reachability in the next internet core is around 40 percent, or the best case is 60%. Latency is about some 20, and BGP coverage is about the longest address about 3 minutes, and the channel the FIE performance bandwidth about a quite significant but acceptable. So a summary. Already works relatively well on the internet core layers, but the problem is associated with the urge. So new insights are needed, and the paper 2 is about the technique or an example. Today's internet is NAT and CityNet centric. We know IPv4 is still dominant everywhere, and CityNet is the de facto mechanism to save the life of IPv4, and still the cash cow, at least in my country, China. Everything we pay is behind this NAT or CityNet. It has many complexities, resources to qualify for the designation architecture on the internet. And none of these complexities work for packets forward, only because the net is stateful. So the path flow state can be rightfully named the root of all evil. And IPv6 again is not a free substitution, because they don't work with CityNet, and they require the customer's equipment participate in the process, and so have little to solve the native networks stuck behind the CityNet. So what Swen can have? Yeah, the idea is Swen has a longer address space, like the IPv6 stateless translations mechanism. So if we trade the path flow state for some little bigger address space, some this state for choke points, so we can make the whole architecture stateless. So the challenge is how to do that that satisfy the constraints. One must be strictly backwards compatible and bi-directional interworking with CityNet, like black TV and black-white TV and color TV, they interwork with each other. The second constraints can be incrementally deployed on existing environment, and not overhaul from scratch. So we designed algorithmic stateless address translation, which is very simple, just embody the private the private addresses in part or whole, the part, the later part, into this is the special form of IPv4 address. For level 4, 3, at least the last 2, 3, or 4. So this is the same idea, and very easy to verify. It's strictly constant complexity in both space and time. So the paper described this architecture. We call it ISP4x for an ISP that is V4 dominant can have an option to upgrade incrementally. The 2 layers translation, like Stateless, and we upgrade them. The first outcome is all these RG nodes now directly interconnected if the ISP allow them to communication. For example, in this is the net in this conference room, and we have another net above in our apartment. They cannot directly connect it, except there's another server, a third party. Now, in this architecture, they can be directly connected without any modification on your phone, on your laptop. So there's some information details. I will skip it for the results, and we have very promising initial results. The latency, the jitter, especially the memory, the accessibility. Memory is constant, almost constant. Unlike the CCNet, when you give 1 million or 100 million TCP connection concurrently, the memory broke from several megabytes to 50 or 100 gigabytes. And this architecture is immune to attacks like this is a very serious issue with traditional serial net. So we think Stateless changes again. Everything can be reconsidered and open a new space for exploration. So we have lots of limits, of course, and many difficulties to overcome. For example, this is a part of the work we need to further address. And open questions. In this, so we have a rule of thumb where you have IPv4, you can maintain it or extend it. And when everything is new, you have to deploy something from scratch. IPv6 is a choice. And so where to start it off? I I have this opportunity, especially express my gratitude and our team to APNet because this is the second year we say something at this venue. And I think it's a very important area, of course. We have so many people, so many economics share so little IPv4 space. India included, and me, my country is very worst to grab a very few IPv4 little space. So can we start here and find some interesting use cases? Maybe next year or somewhere I can report it. And the last one, there may be time to consider Swen another way. IPv4 is full of it's repeated with various patches, and maybe this is the last patch to it. Oh, thank you.
Thank you very much. Let's thank the speaker. Unfortunately, we don't have any more time for questions.
Okay.
Thank you. So I'll just hand it over to Chen and Zhen. This he has control.
Thank you, Sujata. All right, okay, so I think that brings an end to 2 exciting days of APNet. We first thank everybody to stay until the end. This is although quite a bit long workshop, but I think it has many interesting talks and even more exciting interactions between the attendees. So I think we are all very happy to see you all here. And we would like first to thank all the volunteers who made a tremendous job running, helping with the conference. And I think the really good job is really smooth. And of course, we would like to thank the local chair, Liu Xiang, who unfortunately is not here for some other school duties. And all the organizing committee members, the PC members, PC chair, the steering committee, and I think it's everybody's collective effort to make it a successful event. And I would also like to tell everybody that APNet next year will be in Bangkok, in Thailand, co-located with SICOM, which will be a really exciting event with like top researchers from all over the place. So I hope to see you all next year in Thailand. And with that, thanks everyone. See you next year.